Happy Friday. So today, still we are in instruction set for RISC computers, RISC-V, our favorite processor. So last class we covered register instructions, the instructions that working with ILU mostly are register instructions. They work with registers and put the result in registers. They have three actually operand, two operands acting, and result going to go to the other one. We also talk about immediate instructions when one of the operands is constant number. You can have some constant numbers, 12-bit consider constant number. So the maximum positive number, because it's sign, is what? It was your quiz. Yes, yes, exactly. Because with it's 12, but you're going to consider 11 because one consider sign. So with 11 bits, you can have 2047 maximum. And what is the minimum? Minus 2048. This is tricky, but I ask a simple one. You all did right, this one? Almost? Okay. So that's immediate instructions. And memory instructions is for today. Don't know why I wrote this here. Okay. So today we're going to talk about memory instructions. Instructions that working with memory, they are a little tricky because you need to know the structure of memory and you can access every byte in memory. Memory is byte addressable. You know, you can address every byte in memory, even though all registers are 64, 8 bytes. That makes it a little tricky. We're going to see that today. So we mostly going to work with load and store today. For your assignment, I think after today you can do the second assignment. If you want, I can extend it a couple of days later. Just let me know. That's okay because we don't have exam this week, so the next week. So it's okay to. I'm not gonna make a new assignment for you guys because I haven't taught anything new. So yes, so let me know if you want. I can extend it a couple of days before this winter festival break. Okay, so that's what we're going to cover today. Let's go for memory access. So every part that I'm talking about one instruction, I try to explain the block diagram of this processor, how handle actually that instructions. For memory access, that is just two instructions, load and store, because this structure, this computer, RISC-V, is load store architecture. Load store architecture is type of architecture that the only instruction that access to memory is load and store. We have, however, we have load a word, load double word, sometimes load byte, load half word, but we're not going to cover. We're just going to work with word and double word. Okay? So these two instructions accessing to memory, they are slow. Why not make all the systems slow? Because they are limited. Most of instructions are register based. Just these two instructions are memory based. So they are slow, but they're not going to make all the system performance low. Okay. So that's a picture showing a part of the design of this processor that accessing to memory. This is the memory. Memory is not inside CPU. Memory is outside. So this is outside. So that's a memory, data memory. We call it data memory. So as you can see, there is some blue line connected to some parts. This blue line is coming from control unit. Control unit is a main part of the processor that making that just some control data or control signals. These control signals connecting to everywhere. Like for example, this is the control unit connected to ILU, coming from control unit. This multiplexer select coming from control unit. This 0 coming from control unit. This 0, for example, when it's 1, it means ILU get reset. This part showing what instruction ILU doing. So for example, it can be AND or whatever, add, jump, whatever. This is like an opcode. What is this? This is also control for the memory. Even though memory is outside, the part of the control is outside of CPU. We call it control bus. Outside of the CPU, we have address bus, data bus, and control bus. Control bus connecting the CPU with outside of CPU. Okay. Anyway, here ILU doing some operation, getting two input, for example, register, like operand 1, operand 2, and do the operation, and the result can go inside memory or not. As you can see here, we have a line that kind of turn memory. And based off this control unit saying, okay, don't write it in a memory, just write it back to register file. Do you remember we had register file here? Register file is a small bucket full of registers. This is register file. A register file can read two registers at the same time. It's dual reader. So you put address here, this 5-bit address. Why 5-bit? Because we just have 32, 0 to 31. 32 items can be addressed with just 5 bits. So you can address them. This is input, register, 1. This is for register 2, just 5 bits. And for writing, you also have 5-bit to specify which register you want to write, but also you have a data in. The data is 64-bit. The data that need to get written inside this register files is 64. Why? Because registers are 64 bits. They are double word. Double word. Oh, sometimes not writing right. Okay, so that's why memory elements, memory instructions are slow, because they are working with something outside CPU. Okay, so let's see what else we know about that. First, load instruction. Load instruction means we are loading something from memory into registers. So you are accessing memory and bring that inside the registers. So we have two types. We just consider two types. We have more, but we just consider two types: load word or load double word. So accessing memory is based off actually offset and base. Memory is like that. This is memory. each byte of the memory is accessible. You can access to each byte of the memory, okay? Not bits. Bits not accessible, just byte accessible. But you can access these bytes as a bucket of 8 or 4. For example, if you load a word, you're going to take each word is 4 bytes. You take 4 bytes. We can see examples today. And if you do double word, you can take 8. Okay, so for example, load word, this RD offset. I want to see what is this offset means. Register source, okay? Register source, I can put like example, like X5, for example, here. Offset be, for example, 10, and register source is X20. That's the real example, okay? In this case, X20, the address is in X20. For example, this address is in X20. When we put parentheses, it's like pointer. In C, for example, you have pointer. Remember, it's the same way. So so this is like a pointer X20. So this is the address that the pointing this point. But we have an offset of 10. It means we are adding 10, 1, 2, 3, 4 to 10. And we are reading this. For example, here is 0, 1. Here is A5 hex. Here is 0, 2. Here is, for example, 2B, and so forth. So we are accessing to this point, and then we read one word that is 4 byte and put it in X5. But X5 is 16 bit. Oh, sorry. Why is not writing? Is 64 bits. This is X5. But we are just reading 32. So the rest is 0. The rest is 0. And because is the way that we are reading is actually little endian, remember? Little endian. So the address that is less is going to least significant bit. So 0, 1 gonna go here, then A5, then 0, 2, then 2B. Okay, I'm gonna explain it if you didn't get the point, okay? So we have this instruction, we want to see how it works. This is very important. We want, after this class, you learn how read and write in memory using instructions. So the complex part is that you can address and you can access memory per byte. But operations are mostly word or double word, and registers are 64. They are not similar. So how we can manage that? Like this. So first you have offset and base. Base is the base of the address. Offset is how much we add to that, based of byte, okay? So X20 is another register that is 64. Maybe I ask you right now, how big that can be this memory? How big this memory can be? The maximum memory that we can use in RISC-V, how much is that? Because if the address can be 64 bits, you can have a 2 power 64 bytes. So the maximum size of this memory is the max size of memory is 2 power 64. 2 power 64 is a lot. Is exabyte. How many exabyte? I think 16 exabyte. Because tera means 2 power 40, pica means 2 power 50, exa means 2 power 60, but it's still 64. So we need 16 exabyte. 16 exabyte is a lot. So anyway, this is the maximum size of the memory that we can address. Why is like that? Because the address can be 64-bit. So you can have 2 power 64 different bytes, because bytes are addressable. Most of memories in computers are byte addressable. Okay, that's important, very important. Okay, let's go back to this. So we add 10 to this space to find the first of the array that we are reading. How much we are reading, this is specified that. Because we load a word, load W is loading a word. So each word is 4 bytes. So we are reading 4 bytes. These numbers are hex. These numbers are hex. So 1 byte has 2 numbers because hex is 4-bit for each. So it's hex numbers. So we read them and put them little endian. So the first address going to less significant bit and then so forth. 01, A5, 02, 2B. And the rest is empty because we are reading a word, but the destination is a double word. So we put them 0. Easy. Okay, so that was just a simple example for load. We're going to have more examples soon, don't worry. But if you have question, just you can ask me. But if not, we can go to a store. So a store doing the other side. You're writing back from register to memory. Okay? So after reading, you can do some processing and then write that back to memory. So that's a similar type of instruction. Like still you have register here. In load is destination, here is source. And you also have offset, same way. And base, this is base. Base is the base of the address. Offset is how much we add to that. Most of in computer, we are using base and offset all the time to kind of managing arrays. So the array can be modeled using that. That's why we use this type of addressing. A store word, and we also have a store double word if you work with 16-bit instead of 32-bit. This is the type of the structure of instructions. I just need to show that. This is instructions, a store instruction. This is the store. Instruction. And this is the load instruction. Load instruction sounds familiar. Load instruction sounds familiar, isn't it? Is look like immediate instructions. In immediate instructions, we had the same. We had opcode, 7 bits, and then we had registered destination, 5 bits, and then this function that was 3. When we have function 3, it means 3 bits. This function with this opcode play together to specify which operation you are doing. Register source, because we have here register source. Register source is the base, and the offset coming from this 12 bits. Exactly similar to actually immediate instructions. Immediate instruction has this format as well. But immediate instruction has different opcode. That's it. But a store is completely different. In a store, because we have actually we have registers, we have two source kind of source. One is actually base, and the other one is also source. We are making immediate in two parts. Instead of register destination, we have a 5-bit first part of immediate, and then the rest of immediate coming from this part. So we add them together. We attach these two together to make a new immediate for a store. It's a little complex. But how it works is just storing that register to the memory. Maybe you ask me, okay, this register is 64. How you store a word of that inside the memory? Any answer for that? Again, I ask question again. So we are storing a register that is 64-bit to the memory, but we are using a store word. How we can, because word is half of the double word. Okay? So how that works? Any idea? There is a little contradiction here. Again, I'm asking question. We are writing a double word register using a word store. How that works? Yes?
Are you just storing the last half?
Yeah, you just use the first half, actually. Yes, just use the first half. If it's double word, it doesn't matter. A double word is like two words. If this is least significant bit, so you just use this part of that. And this part, you don't care. Whatever was there, you don't care. You put this in the memory. Okay, so we can see more examples soon. I also have this type of notation for the structure. This is exactly same as this, but in a better style. So this is called S-type store, and this is load, but because it's in the same style as immediate, we just cover that in immediate type. Okay. That was just general idea how these two instructions working. Let's go more details. Offset addressing. So as I mentioned, because we want to model, arrays and vectors in computers, we're always working with the base and offset. That's how we access memory. In computer, we always use using this method. Always have a base and offset. And we add offset to base to find actually proper address that we will need to work on. Okay? Okay, so let's see how we can find effective address. We just need to add them. So the effective address is called effective address. Effective address is a base address plus signed offset. Okay, so one important point mentioned here, signed offset. So it means you can jump up and down in memory. If you jump up, you can access anywhere around that base, top of the base, down the base, because the memory is like that, as I mentioned. So this is the memory, is byte addressable, and this is the base, for example. So you can jump up or jump down. That's possible. So you can play any way that you like. Let's do example. Okay, this example is load a word. Okay, so we have a memory, byte addressable. We have a, let's see, oh, we have more information about it. We have x5, that is base, is this value inside the x5. Okay, so as you can see, x5 is double word, but we just put here this hex number. It's just a piece of that. The rest is 0. So if I want to write all the x5, so here 0, 0, 0, 1, 0, 0, 0, 0. This is one word. The other word is also 8. This word is all 0. So this becomes a double word. So this number coming to this part, okay, least significant part. The rest is 0. Just to see how we understand that. So x5 is the address. This is, here we put the address that we want to go, base address. So for example, this is somewhere here. This is the base address. This is the base address, 1000 hex, and the offset is 12. So it means 12 bytes after. So this is 1, 2 to 12. And we don't know what is here, but imagine here is some information. Something like that. Hex. Because it's hex, you can have A, B, C, D, whatever. So this is 12 x5. Okay, what's gonna be if you add 12? 12 is C. If you add this number, if you add these two together, the result's gonna be C001 all 0. So this is the new address that we want to load. How much we want to load? 1 word. Why 1 word? Because we are using load word. We can use load double word. That's a word. And where are we gonna put it? X10. So X10 is destination. So in X10, we're gonna put this 01, 20, AF, CD, 00, all 0. 8 zeros. Each of these numbers, because they are hex, 4 bits, they're gonna have 4 bits. So 8 of those gonna be 32, that is 1 word, and 2 of that is gonna be double word, 64. Okay, so in digital logic, you play with these numbers a lot. So if you don't remember them, go back and review and learn, remember them. We're gonna use them a lot in memory access, but they're all hex numbers. Hex numbers are easy to understand. Okay, so I have the better version of this. So that's the base address, and we find immediate offset, that is C, that I also here, and then we find effective address when we add them together, and when we read that here, we don't know what is there, but imagine those information there. So we put memory of this inside extend. So this is going to be in extend. If those stuff are in the memory, we are just imagining this stuff in the memory. It's like the method that we are using for pointers in C. Here we are doing that. This is like a pointer. Pointer is the address that you want to access and read from that. But that pointer has some offset that we add with the base to find exact effective address. Effective address is the place that we are trying to load from there. Okay, that's actually, that was one example. Let's go to this one. This is for a store. I already explained here. We just gonna repeat that. A store has this format. We have 7-bit opcode. You have 5-bit first part of immediate, and then rest of the immediate is here together. It's going to be 12 immediate. And then this function that is 3-bit, this function and this opcode acting together to specify which operation you are doing. And you have two sources. One source is the base, and one source is actually the value that you want to put in the memory. Okay, so example like that. Let's draw memory for this example as well. So we have X9. Let's see if there is more information about. There's nothing there, so we can just consider this is the memory. So you are, and the memory again is byte addressable. They are bytes. Okay, each address belongs to 1 byte. But the base is X22 address of that. When we put parentheses around X2 is like a pointer. This is the address. Okay. So that's a base, but 96 byte after that. So imagine this is 96 bytes after the bytes. That's important. This is bytes. Maybe you don't get how important that, but when you do multiple example, you can see this, these notations are important. Anyway, we are here now. So this is 96x22, like address of that, like this, for example. And then we are storing x9, but it's double. This time is double. So I didn't mention what is inside x9, but you imagine in x9 we have this number 0, 0, 0, 0, 0, 0, F1, 0, 0, 0, the rest 0. All 0, just these two parts is 1F, for example. Okay, so how we fit this here? So it's going to be longer, but 0, 0 here, 1F here, and the rest also 0. It's going to be 8 bytes. I might ask you in your exam to draw this, so you need to understand what's going on here. You need to understand this part. Okay? So any question about this? Like why here is 8 bytes and the other example was just 4 bytes? Because of this. This is a store double. The other one was a store word. Okay, double word and word. Okay, that's a store. Oh, we're done. Time. Okay, just this is another example to showing how we put a store in the memory. This is important when you have two parts and you need to attach them together to make actually effective address. So in this example here, I don't know why it's wrong. It was 51. It's 35, because if you put this, this is 35. 35 is an opcode for a store. And we have two immediate part, 5-bit from here, 7-bit from here. We put them together. This becomes offset. And we add this offset to x2 to find effective address. And then we actually store that value that is a double. That's this address going to be the start of that. We take 8 bytes and put it in x10. OK, I think there is no more time. With this example, we can do next time. But this exam is actually very similar to one of your assignments that you might be able to use that. So the only thing that's important in that is that's a C code that use array. You are kind of modeling array using assembly code. It's not difficult. So we can talk about that next class, Monday. Monday, we have a class here. But Wednesday, the class going to be online. OK, have a good weekend and day.
Yeah, you're